So next we're going to go to our next speaker. So I think James is also in Eastern time, and it must be awfully late for you, James. So do we want to, maybe do you want to go next? Would that be okay with you?
Sure, I'll be happy to go next.
Yeah. Okay, sounds great. All right. So James Boyd is going to talk about something really exciting that we talk about here in the lab, about how these creative machine models and machine learning can be used to do math and science for us. So, so far we've talked about creativity in art and in photography and images, but so far we haven't necessarily talked about creativity in exploring mathematics and science. So yeah, we're really excited, and I'm just going to hand it over to you, James. Take it away.
Thanks so much, Alyssa. Can you hear me?
Yeah.
And you can see my slides?
Yep.
Okay, wonderful. Well, then I have no excuse not to begin. Okay. Hi, everyone. So my name is James Douglas Boyd, and I'm the CEO of the Wolfram Institute. And as you can see, the title of my slide, or the title of my intro slide, the title of my talk is Can Machines Invent or Discover Mathematical Objects? A Philosophical Foray. So without further ado, let's begin. So I might begin just with a background remark on computation and mathematical proof. So computer-assisted proofs and automated theorem proving are gaining prevalence within mathematics. And this in turn, at least in my opinion, should motivate wider conversations concerning human-computer interactions that are mathematical in nature. And I think a key principle to keep in mind when considering mathematical human-computer interactions is intelligibility, and I suppose for purposes of this talk, given the theme of the workshop, human intelligibility. So at present, humans face the challenge of explaining mathematics to computers. So for instance, a proof assistant such as Lean. But with time, I imagine that we will increasingly face the challenge of understanding the mathematical results that machines themselves produce. We know, or at least those of us with some experience in this area, we're familiar with scenarios in which it appears as though machine proofs resist human understanding. But perhaps machine mathematics can indeed be intelligible as a general matter. So we might like to know if, for instance, beyond computing proofs, machines can invent or discover new mathematical objects. After all, mathematics involves more than proof alone. It also involves, for instance, theories and objects which simplify proofs and also themselves carry mathematical beauty. So I might make a claim. I'll make a few claims throughout this talk, if you'll permit me. I'll make a first claim, which, in my own opinion, I think if machines compute new proofs over time, let's say, without the support of new theories or objects, I think that such an enterprise will come to strain human intelligibility with time. And if you've seen messy, elaborate machine proofs, I think you'll kind of understand why. Okay, so I'm claiming that it'll be important to create objects. Okay, so how do we invent useful objects? That's kind of a key question in this talk. So I'll make another claim while I'm at it. So I would say that machines can only really invent or discover useful mathematical objects if we can teach them a general method for finding useful properties. And the usefulness of properties of an object is demonstrated only as we do things with the object. So in order to help concretize our discussion, I'll invite you to entertain two philosophical persuasions. So one is known as constructivism, and the other one is known as perdurantism. So constructivism is a persuasion in mathematics, and constructivists are inclined to award recognition of existence only to those mathematical objects whose construction can be executed by a known procedure. So if they can't specify how they might build an object, constructivists hesitate to presuppose its existence. And actually, constructivism lends itself to computational interpretations, for these constructive procedures can themselves be algorithmic. Now, perdurantism is a persuasion in metaphysics. So perdurantists inquire into the manner in which objects persist and change with time. So perdurantists ask if ontologies are, at least in part, temporally contingent. Um, Now, we do not entertain a notion of time in mathematics, like in pure math, but we can, I would assert, consider kind of a perdurantist mathematics that's attentive to objects as they're acted upon by operators, mappings, and functions. In other words, mathematical objects certainly do change. We can change them, and we can study that. And I think that that would be a kind of a perdurantist turn, I'll explain why I think that that could be important. So why don't I just make another provocation? So at least in my opinion, in my experience, the most enchanting mathematical objects are those whose properties are understood in view of the application of mappings or operators or functions to such objects. So such objects either survive these mappings or operators or functions, or they kind of emerge following the application. And the really interesting ones carry essential data that is of interest to mathematicians. So I'll give some examples. I hope you don't mind if I give some examples. So the first example is something known as the Galois group, which was actually invented by a very young French mathematician who died at age 20 in a duel. Um, anyway, Galois groups are groups of automorphisms of field extensions that happen to fix base fields. So these groups capture the ways in which a kind of a field extension can map onto itself whilst preserving certain kinds of algebraic properties. And just as a kind of a technical aside, these groups are under certain conditions generated by these things called Frobenius endomorphisms. And I only mention that because I'm going to mention it one more time momentarily. That's one kind of example. Another example that's I find to be visually quite stunning and arresting is the Hecke eigenform. So Hecke eigenforms, and some examples being like Eisenstein series or Cuss forms, these things are eigenvectors for all prime index Hecke operators. I won't explain what a Hecke operator is, but under these Hecke operators, at least the prime index ones, these eigenforms transform only by a scalar. So they only change by an eigenvalue. And so when you apply operators to these kinds of forms, they only change by a scalar, and so you get what's known as a spectrum. So you get a kind of a set of eigenvalues that they happen to nicely encode data regarding the solutions of polynomials over fields. So I like to think of a spectrum as essentially you're applying some operator to a form, and the spectrum shows kind of the way in which the form changes while still remaining the same. So basically, under the transformation, it's the same. The only thing that changes is a kind of a scalar value. So that's, I think, an interesting example of something kind of staying the same, but also changing with time. Okay, now I'll kind of maybe legitimate that comment I made about Frobenius earlier. It so happens by this thing called Eichler-Shimura correspondence that the spectrum or the spectra of these eigenforms and also the values fixed by these Frobenius endomorphisms that I mentioned on this slide, they actually happen to capture the same arithmetic data. They actually capture the same data about solutions to polynomial equations, which is very surprising. It's relevant to things like Fermat's last theorem, as well as the Langlands program, which I work on. I also just mention it to mention Shimura, which is who is a very good Japanese mathematician. So I thought I would do that too. And if you'll entertain a little more math jargon, I will also mention just two other eigen examples. There's this thing in mathematics called there are these things in mathematics called motives. This mathematician Alexander Grothendieck, he advocated for this theory of motives or motifs that kind of capture the cohomology of algebraic varieties. And in the Langlands program, we treat motives as these eigenspaces of correspondences between these varieties that are also extracted via Frobenius endomorphisms, and then we construct these kind of functions from them, which are they're kind of like Riemann zeta functions, but kind of a little more sophisticated. I'll also just mention these things called eigenbranes, which appear in the work that Witten and Kapusten have done on geometric Langlands for d equals 4, n equals 4, super Yang-Mills theory. As kind of a general principle, I'm somewhat skeptical about branes just because they kind of act on these arbitrary pre-given space-time manifolds. And so there's kind of issues about background dependence, background independence. But the fact that we have these kind of eigenbranes that have this kind of perdurant quality to them, I think is kind of interesting. Okay, now let's get back to some philosophical questions and the question of useful objects and how we could perhaps understand what it means for an object to be useful. So there are many questions that can be asked. I'm just going to ask really kind of one or two. So one is, now that we know something about constructivism and also perdurantism, like, is the constructivist view of, I've said invariant structures, but that's actually a typo. This should say persistent structure. Is the kind of constructivist view of persistent structures in mathematics, is it also kind of perdurantist? Like, can we only prove mathematical properties, say computationally, by demonstrating how objects persist and change with time? So that's a kind of example of a philosophical question you might ask about objects and their properties and how you might subject a computational treatment to them. This question is intended to encourage a kind of a broadening of constructivism beyond the mere question of the existence of objects towards these additional questions of their useful properties. And I think it's important that we develop a framework for understanding not only how objects are constructed computationally, but how their properties are proven computationally. And of course, this will also involve a kind of a taxonomy of properties and when they're useful and when they're not useful, because I imagine as soon as we try and experimentally determine if machines can produce objects, I'm sure that they'll produce a litany of useless objects. So we'll have to try and understand which ones are useful and which ones aren't. So this kind of latter approach, I suspect, should involve some framework for understanding the manner in which objects persist and change under things like mappings or operators or functions. And I think this invokes, I think if you already have a kind of a constructivist point of view, you also find yourself provoked by questions of perdurantism. By way of concluding, I might simply confess that this presentation did not succeed in making clearer the question posed in the title, but I think given the time constraints, any attempts to do so would have been shameless and inconsiderate. But if anything, this presentation, I think, has conveyed the difficulty of the question of how useful objects are to be invented or discovered in mathematics, actually by humans or machines. And it's reviewed the question as a matter of design, philosophy, and of course, mathematics itself. And it is hoped, and when I say it is hoped, I mean it's my hope, that interdisciplinary considerations can help to foster a practice in which machines are used to develop human intelligible math. So thanks for your time.
Yeah, thanks. That's super interesting. And a lot of the themes that you had presented about usefulness and objects being a result of these interactions reminds me a lot of the last session that we had. So I love that all these themes are overlapping between the different sessions. It's really exciting. So yeah, thanks so much. All right. So the next question in the Slido is for James. So constructivism plus math may enrich our way to handle computational proof by discovering invariants and properties. So what should scientists aim for first?
What should scientists aim for first? Well, who am I to say? It depends on what they want to do. I mean, if it's a question of if the question is what should scientists do in pursuit of this possibility that was outlined in the talk, for instance, developing some computational capability to do mathematics beyond just proof without further development of theory or objects? Well, I mean, I guess the first modest thing I would say really is I've introduced constructivism and also predurantism just as examples of philosophical schools of thought or persuasions that I think are relevant to this kind of design, engineering, technology development question. And the first thing I would recommend is just raising more of those questions. I mean, the questions that I raised in my talk are not exhaustive. And this is kind of my instinct in general, which is I like to say that philosophy is what you do before you do anything else. And so, in the world of philosophizing, you're not constrained by path dependence or kind of ratchet effects, or you haven't done anything yet. Technology hasn't been developed yet. So I think it's important to just think through what do we understand? So, let's say you're a mathematician. Do you really understand what you're doing? I mean, do you let's say there's some mathematical object that you like. Do you know why you like it? If you had to compare it with some object that was useless, can you precisely explain what, as a general matter, kind of methodologically, why this object is helpful and this one isn't? And I think if we start with ourselves and we try to ask, kind of like kind of like what an anthropologist would do if an anthropologist was looking at contemporary mathematicians. Do we have some sort of anthropological explanatory or descriptive power over our own practice? Because if we don't, then I very much doubt we'll be able to impart any of the methodologies that we ourselves practice to machines. Okay, so those are actually some suggestions in terms of ways to start, that's again why I'm recommending something that's quite interdisciplinary. Because on the one hand, we're doing mathematics. On the other hand, there's a design prospect and design promise. And going from one to the other, I think involves things that like what you would do in ethnography or anthropology or philosophy of math or philosophy of science. And then you have to think about the consequences, and then it becomes almost a policy thing, which I think also applies to the sciences. So that's what I would recommend. Basically, keep thinking, and let's think more about mathematics before we simply start kind of rushing to create machine mathematicians.
That's going to be difficult.
It's not even clear it's possible, right? Yeah. It's not even clear. It's not even clear that it's possible. That's why the title of the talk was a question. We don't really know what machines can do in the future, and when it's not clear how much self-understanding we can develop either. But it's worth thinking about.
I mean, I'm mostly on your side anyway. I think also it's because it's more interesting to think about these things than to actually try to make a machine. But I'm not sure whether, I think maybe it will turn out that somebody's gonna make this machine that creates new math before we've thought it through. I think somehow this seems to me like it's gonna be the more likely outcome. I don't know, but. Yeah, maybe this is a case where we have to understand something first, and then before we do it. But recently, that hasn't seemed to be true that much, I guess. What do you think? You think we are gonna understand first? Don't you think that the machines are gonna get there first, or that somebody's gonna make a machine before we really understand maybe what are the nice properties of mathematical objects?
I mean, so I suppose if there was a scenario in which essentially some black box happens to simply produce miracle objects, we don't understand how it does so, but it's performant and for whatever reason it's able to produce the objects We don't understand how it produced them, but it can explain them and we can understand them. In that scenario, it's kind of from a utilitarian perspective, I suppose it's nice, but for something like mathematics, which is really just about pure inquiry and deep understanding, I would say that, you know, I mean, to be candid, right? AI for the most part has emerged as a consequence of economic and governmental incentives, where it's not really necessary to have deep understanding. You just have to have some sort of outcome, like things are more efficient, or services can be provided more cheaply, or different political objectives can be achieved in some desirable fashion. Not necessarily about deep understanding. So I would say, you know, if kind of techniques that have worked in a market setting are now applied in the sciences, and there's this kind of like high output rate and people enjoy it, you know, I worry that it'll actually just turn some of these areas of pure inquiry basically into just consumer societies. And I wouldn't like to see that if people more or less if mathematics, because you can imagine that type of scenario, your mathematical skill would just give you good taste as a consumer. So you would probably even stop doing mathematics, but you know enough mathematics to be able to appreciate these works that are being developed by machines. So then you're like in the same position as like a film critic or an art critic or like a wine connoisseur or something, where you basically now have like a market for pure thought, pure objects, and you're not even really making them anymore. And you have no idea how they're made, but you know enough mathematics to kind of still appreciate it. And I kind of, so that's, I haven't actually thought about this at all before, but that would be my position, which is if we don't have understanding in how machines do, you see, in other things, even like physics or biology, it's different. I think especially in mathematics, if we don't really understand how the thing is being done, like, it doesn't necessarily have to be the process of how the machine is developing the objects, but if we don't understand the way that the objects are actually formed, if we don't understand the process of how the thing was invented, then I think it becomes kind of a spectacle, and it becomes too close to a kind of a consumer society to really resemble the intellectual culture we have today. So that's kind of a societal comment of hesitancy.
Yeah, I'll read a comment from the chat from Olaf, but then after that, I want to go back to a question for Petra, and then we can open up for just general discussion amongst everybody who's here, and just go ahead and just have a chat. So Olaf has been saying one thread about something that you mentioned, if I understand well, about the needed continued effort to build theories that are aligned with human understanding. This aligns nicely with something that he's heard or read from Shinwei, who spoke at the workshop this morning about family resemblances, or what he himself calls Wittgensteinian math versus universal math, in case he's mentioned that to you before. So he wants to unpack that a little bit. It's his way of taking a shortcut in explaining the view under which some mathematics are self-referential and can be further derived by a contextual computer, but may lose alignment with human mathematics as they may not be framed under the same perspective as the mathematics that we know. As such, these are just mathematics that can be versus a different set of universal mathematics, which can be defined as being universally possibly communicated between any two agents in the world. He's not sure it connects very neatly constructivism and perdurantism, but it seems to do so as a Platonic versus modern theory of mathematics living on top of physics. Arguably, this will require a lot of effort to maintain diverse philosophical viewpoints going forward into a digital creation-augmented society. And without that diversity, we might be stuck in a mathematical complex analog of obscurantism, like people were before astronomy, before Copernicus. So, yeah, that I just wanted to make sure, because he's, because he's not, he can't chat. I wanted to make sure that also the YouTube live was able to see the really interesting conversations happening there.
I'm reading Olaf's comment one more time.
Yeah.
Well, this gets into a whole other thing, but I would like to think that if 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 machines are doing mathematics of any kind, in principle humans could also understand it. And I think I'm basically operating under this presumption that if the theories are nicely kind of compressed with nice, sorry, if the proofs are kind of nicely compressed with nice theories and nice objects, this is kind of my view of like nice mathematics that humans tend to pursue. Whereas if you look at a machine proof, these proofs can be quite messy, but the machine is quite capable of keeping track of them. So this is one kind of pretty likely outcome, especially over the short term, is you just have these very large, unwieldy, aesthetically hideous, but nonetheless correct proofs that are coming from machines, and humans have a very difficult time following it. So, yeah, I think that this is I think it's a problem, and that's why I think that in general, creating objects and theories that help to kind of compress mathematics is kind of pursuant to the Occam's razor or kind of principles of parsimony. That, as well as questions of translation, duality, correspondences. I actually showed one with that Eichler-Shimura example. I think those are quite important as well. Especially in futures where I mean we already have it today in mathematics where people are, or in science in general, where you have specialization in many different areas. And you have to find some connective webbing between these in order for people to be able to understand each other. That will also happen with machines. The question is, if machines are producing messy, long, complicated proofs, how can humans understand it? I think that they can, but I think that will in its own right require some techniques to be able to kind of translate and probably compress the kind of work that machines find to be perfectly computable, but humans find to be relatively unintelligible.
I didn't really understand the proto-rantism, but it sounded interesting.
It's not even easy to pronounce. I actually was practicing pronouncing it before I began my talk because I was really scared of mispronouncing it. Basically, the idea is it's not just enough, like just constructing an object is not necessarily sufficient for understanding whether or not that object is kind of useful or interesting. You also want to know, and I'm going to use some informal language, like if you put that object in some interesting mathematical environment where things are happening to it, do you get out something that's kind of distilled? So like, I won't get into the details, but the examples that I showed, like with eigenforms and Galois groups, this is like, harvesting out like syrupy kind of nectar from these mathematical objects. It's like this pure kind of quintessence of the data that you want, and everything else has kind of gotten operated away. And so that's what makes them useful. They're useful because the seeds, the actual fruit, they can actually be kind of harvested from these objects, and everything else, the husk and the inedible parts, get kind of thrown away. Maybe I should have used some more informal language like that, but that's the kind of idea. Is if you just tell a machine, go construct me some objects, they'll give you. I mean, I imagine there can be all kinds of junk that we wouldn't really care about. So I think we have to philosophically understand beyond just the construction of the object. We have to find some way to describe philosophically what kinds of like we have to have some framework for studying objects of interest to us.
Yeah,
if it's just about objects, we're going to get a litany of junk probably.
Yeah, I think that part I understand. I'm just trying to figure out a little bit more what exactly the proto-rantism, because like I guess my intuition was always, okay, we want objects that we can use in as many proofs as possible. So basically, if you have some construction and then this construction pops up in many proofs, then it's a good one.
This proto-rantism thing is not. It's not. I shouldn't make it sound more complicated than it sounds. often philosophy in metaphysics is really quite simple. It's just a distinction between, are we going to think about this object as some Platonic thing that just is kind of an entity in its own right, and that's it? Or are we going to think of it as some sort of an object where, you see, it's complicated because this is a concept that really originates in metaphysics. So usually people are thinking about what happens to these things in time, which is kind of, I won't say it's straightforward, but it's somewhat straightforward. Mathematics is different because, as I mentioned before, it's not like there's time in mathematics. But I think the best kind of analog of time that we have in mathematics is that we do things to mathematical objects. So a mathematical object doesn't just sit there. It participates in different kinds of operations. You could think of it as being on some assembly line, and we're kind of doing things to it. And so that's the kind of the image I have is, if we have some method for understanding, you have some object that's being in an assembly line, or you're putting it through some process, and you have different things that are coming out to, you have different things that are happening to it. Then the end product is something highly desirable. Again, like I'll use the analog of like a syrup or a nectar or something that's kind of pure and encapsulates exactly what you're looking for. That's I'm invoking this term from metaphysics, but I'm at the moment, because there's no theory, I'm basically using it abusively. But I think that a theory could be developed in order to help explain it. Yeah.
Okay, got it a bit better.
Perfect. Yeah, and we can continue this discussion on the Discord too. I think that it's a really interesting topic. Well, I think with that, I think let's thank all of our speakers. Thanks everyone so much for the first session and the second session. Yay! Yay! All right. So yeah, our next and final session of the workshop will be on Friday, 9 p.m. Japan time, 8 a.m. Eastern time in New York if you're in the United States, and other time zones in between. So please join us there, and we appreciate you joining us today or seeing the recording, and we'll see you then. Bye, everyone.